Good morning and good afternoon, everyone. My name is Dr. Ajay Reddy Sattu. I lead product marketing and product line management for Industrial Power Division. Our focus is energy infrastructure markets, including solar, energy storage, UPS, electric vehicle charger, and segments. I manage both silicon IGBT and silicon carbide based discrete and module solutions. Today I would like to share few thoughts about emerging electric vehicle charger market, system trends, and onsemi's comprehensive solution to address this market. Perspective. Key factors driving EV charger market is global push for decarbonization. In the context of IEA's net zero mandate, this is addressed in many sectors such as energy and heat, transport, building, and industry. Advancements in battery technologies pushing cost and resulting in growth of electric vehicles is presenting a strong argument for charging infrastructure growth. At the moment, most of the demand is seen from the light passenger vehicles, but in the near future, we expect demand to be coming from mid-duty and heavy-duty vehicles as well. Quantitatively, overall power semiconductor opportunity for suppliers was around 220 million in 2022, and it is growing at a CAGR of 15.3% with nearly 700 million by 2029. Similarly, shipments or installations are also expected to grow at a CAGR of 12% in the same period. Installations are characterized by the system power such as less than 50 kilowatt, 50 kilowatt to 150 kilowatt, 150 kilowatt to 350 kilowatt, and above 350 kilowatt. Other key thing to note is how the installation segment by system power will evolve. Today, installation or availability of charger pools with wattage more than 150 kilowatt accounts for nearly 32%. And this will double by end of the decade, accounting for nearly 64%. This presents an appealing market opportunity for power semiconductor suppliers. While the market is appealing, it's important to understand what the landscape is, who the key stakeholders are in the entire value chain enabling charging infrastructure market. Service providers include not just standalone entities, but they also include other stakeholders such as utilities, fleet operators, service stations, and vehicle OEMs. The initiatives and the business objective taken by each of these stakeholders shines a light on what can be expected in terms of system trends and deployment plans. For example, utility company such as Enelway has been forefront in enabling highway charging in Europe, while State Grid and China Southern are accelerating the same in China. Similarly, shifting from oil and gas to electric vehicles would render many of the existing service stations useless, and so we are seeing push from Shell and BP to venture into enabling their service stations to offer EV charging as well. Finally, major EV manufacturers such as Tesla and VW are also in the forefront enabling charging networks such as Tesla Supercharger Network and Electrify America respectively. We also see a significant push not just for the light passenger vehicles but also the medium duty and heavy duty vehicles as well. Here we see Daimler Truck, Volvo Trucks, Milans, etc. as part of the value chain. Finally, at the bottom we see many EV charger power block global suppliers who work with downstream stakeholders and upstream suppliers such as onsemi. It's imperative for a key supplier such as onsemi to understand the motivations and objectives of key players to position its technology and product roadmaps. Chargers of today fall into three main categories, separated mainly by their power level. Level 1 is at 120, typically comes from household outlet with maximum current rating of 12 amps and can add 3 to 5 miles per hour. Level 2 is at 220 volt, available at home, workplace or public locations, and can add up to 12 to 80 miles per hour depending on the power output. Level 2 chargers can deliver up to 22 kilowatt or so, making them capable of charging the average EV in about 2 to 8 hours. The limitation is mainly from the vehicle side in terms of the battery capacity. Bidirectionality is a possibility, with vehicles offering this with bidirectional onboard charger. However, in level 1 and 2, there is not much power content for suppliers. In DC charging, there are multiple different ways. It could be DC wall boxes, which are becoming common in residential and public places, which can deliver up to 22 kilowatt. In commercial space, there are mainly two segments: commercial mid power up to 50 kilowatt and commercial high power, which can go up to 350 kilowatt. With DC charging, the time to charge is much better than AC chargers, and these systems can add up to 100 miles or more of range to an EV battery in about 30 minutes. Now, in terms of different modes at which these vehicles are charged, in general, this can be divided into two modes: constant power and constant voltage. When the battery state of charge is low, the batteries will be charged at much higher currents, allowing the vehicle to reach up to a reasonable 70 to 80% state of charge, and then a constant voltage mode is used to charge the rest of the battery. State of charge information would be relayed back from the battery cells via a battery management system to the electric vehicle and to the DC fast charge station. When we think about system design and application trends across different segments such as DC wall box, DC fast charger, very fast charger, and megawatt charger, key considerations such as cooling type, package housing of power solutions, mission or application profiles, different modes of operation, environmental conditions, modularity, scalability, and bidirectionality come to mind. In terms of cooling, the lower power DC wall boxes and mid power DC fast chargers up to 150 kilowatt can be used with air cooling. However, for the higher power DC fast chargers up to 350 kilowatt and above, liquid cooling is preferred over air cooling for improved reliability. The obvious trade-off is the upgradability at the cost of reliability. Liquid cooling results in a closed-loop system but improves junction temperatures of the devices, thereby reducing the aging effect and improving solder joint and wire bond lifetimes. Similarly, different package housing are also used, discrete or power module solutions, depending on cost, performance, and reliability requirements. For the lower power options up to 150 kilowatt, discrete packages are preferred, whereas for the higher power blocks, power modules are preferred. Regarding mission profiles, DC wall boxes typically can see anywhere up to 20,000 cycles over its useful life operation. While the mode of operation is also well understood, they are very well controlled environments in people's garages. Whereas if you look at all fast charger applications, these cycles can be anywhere from 75,000 cycles to more than 100,000 cycles, and the modes of operation can be very different depending upon the end user cases. And all of the DC fast charger applications will see environmental conditions that are quite harsh and can be anywhere from negative 45 degrees centigrade to positive 55 degrees centigrade. Modularity and scalability of the DC wall boxes is non-existent, but for all the other DC fast chargers, it is a preferred option. Finally, bidirectionality is also becoming a very common trend to enable vehicle to house and vehicle to grid, helping in peak sharing and load sharing. Let's take the example of a DC fast charger and talk about at the system level. On the front end, there is a three-phase power factor correction boost stage implemented in a variety of topologies such as 2-level or a 3-level, and it can be a unidirectional or a bidirectional topology as well. The voltage level from the grid, 400 volts in EU and 480 volts in US, can be boosted up to 700 to 1000 volt and can also be higher in future. A subsequent DC-DC isolated stage converts the bus voltage into the required output voltage. The output voltage aligns with the EV battery voltages, typically 400 today, and we are increasingly seeing 800 volt as well. And that needs to cover a wider voltage charging profile. Therefore, the DC-DC output might range anywhere from 150 volt up to 1000 volt. Specific implementations might be used for 400 volt or 800 volt level. Beyond the main power devices, gate driver ICs, power supply ICs, communication transceivers, op-amps, etc. are also part of the system. Communications are very critical, especially between stacked modules on the power between vehicle and charger for the charging sequence using Bluetooth, Wi-Fi or Ethernet based standards such as 10BASE-T. There are standards and protocols such as IEC 61851, SAE 1772 standards, combined charging standard, or North American charging system or Tesla supercharger protocols. Based on the system design, application trends, and the generic block diagram that we have just looked at, key design trends at the system level are outlined on the left side of the chart here. A wide output voltage range from 150 volts to 1000 volt is needed for supporting many different battery voltages, and then of course we have seen the trend of shift to the higher power in commercial mid to high power chargers. Moreover, there is an aggressive shift from silicon IGBT based solutions to wide bandgap silicon carbide technology for higher thermal conductivity and power density. Obviously, given the fact that we are moving to higher power charging stations, module solutions are also preferred when size and power density are at premium. And then finally, we are looking at shift from unidirectional to bidirectional, and that is to enable vehicle to grid applications for peak load shaving. For safety, reliability and compliance standards, there is a requirement for isolated gate drivers as well. While the premium on the smaller footprints, performance and power density is understandable, many customers are also looking at design for reliability too. On the right side of the slide, I present some key topologies that are used in current EV charger power stages. 3-level TNPC, 2-level half-bridge or interleaved PFC are used for the active front end, while half-bridge and full-bridge topologies are used for the DC-DC output stages. This is not an exhaustive list of topologies. There may be many other choices depending on system requirements. 2 slides we will look at power semiconductor solutions and what the typical trade-offs are for discrete and module solutions across power classes. Between discrete and module at the system level, designer would need know-how when using discrete devices, and this approach generally results in larger PCB area. With the power module approach, this task becomes easier and overall component count is also lower, improving manufacturability and system size. From a performance perspective, when we look at thermals, power modules generally offer lower thermal impedance than discrete solutions, leading to lower failure rate. Electrical isolation would have to be implemented via isolation pads if discretes are used. When multiple dies are needed for power scaling, die selection and die matching is easier with modules, whereas in discrete solutions, this would require a lot of additional effort. Given these guidelines, however, we see both approaches for system design in the mid-power ranges. As the system power increased from 50 kilowatt, stacked solutions are used with power blocks ranging from 20 kilowatt up to 100 kilowatt. Industry standard packages such as TO247 and D2PAC 7 lead are used, and a preference for top cool discrete packages is also increasing. On the power module side, Industrial modules such as onsemi's F1, F2 and F5, which comes with a base plate, are also pursued heavily. Along with the power semiconductors, onsemi also offers a wide variety of isolated single channel or dual channel gate drivers, and some of the examples are shown on the right side of the chart here. Now let's look at solutions enabling 22 kilowatt to 350 kilowatt for EV chargers. Looking at the loss distributors for a typical power block, nearly 70% of the losses come from power semiconductors. Given this premise, it is clear that silicon carbide is the obvious choice of technology over traditional silicon IGBT technologies. In this case, onsemi's Gen 3 silicon carbide 1200 volt diodes offer industry-leading performance optimized based on forward surge current and reverse recovery. Similarly, our Gen 3 MOSFET platforms are also optimized to cater to various end markets aptly, meaning for higher frequency switching applications such as EV charger, we recommend M3S technology, and for traction or motor control applications, we suggest M3P or M3T flavor, which highlights short circuit withstand time. All of our Gen 3 diode and MOSFET based solutions are released to market, and more information can be found on our website. With silicon carbide implementation, system efficiency can be improved by nearly 3 to 4% over silicon solutions, increasing power density for the same footprint and reducing charging time. Improved efficiency with silicon carbide comes from lower conduction losses and lower switching losses, which also simplifies cooling requirements. Since air cooling is still in the majority, fewer cooling fans and thus lower ambient noise is also expected. On this slide, I would like to present onsemi's Gen 3 MOSFET called M3S, benchmarking against some of the global competition. There is a good presentation of both planar and trench technologies on this slide. The comparison is done for a 40 milliohm RDS(on) rated device in a standard TO2474 lead package. Comparing DC characteristics or RDS(on) performance at VGS 18 volt and junction temperature of 175 shows that onsemi has a competitive RDS(on) compared with competition. However, if you look at the total switching losses curve at the bottom left, onsemi is by far the best performer. Better switching loss, especially for turn-on energy loss due to lower ERR characteristics and smaller device capacitances. Similarly, if we take two competitors A and C and observe the turn-on and turn-off waveforms on the right side of the slide under same switching conditions, the charts at the top show waveforms during turn-on, and you can see smaller peak current for the onsemi devices, and this is related to smaller ERR and CGD, and additionally peak-to-peak ringing current is also lower for onsemi's M3S than other competition during turn-on, translating to better EMI performance as well. If you look at waveforms for turn-off, differences are not so visible, so we could say that there is very similar performance between M3S and competition. Using the same Gen 3 MOSFET devices in power modules, we have simulated a 50 kilowatt active front-end block using one of our 11 milliohm TNPC module in F2 package. For the full three-phase, 3 TNPC modules were used. The simulation conditions are shown in the middle of the slide here, with input voltage at 400 volt line to line and switching frequency of 20 kHz. Heatsink was kept at 90 degrees C. For the 11 milliohm module, at this frequency, junction temperatures were around 125 C and power stage efficiency was 99%. Obviously, there will be a trade-off on the switching frequency used, cost of inductors, and the efficiency of power stage. For example, using the same module, if we target higher switching frequencies such as 48 kHz, inductor value will be less than 500 microhenry and can achieve close to the same efficiency, 99%. However, maintaining reasonable junction temperature will become important to manage aging effect. In a nutshell, Higher switching frequencies can help with smaller magnetics and system cost, but can result in slightly lower efficiency and also slightly worse reliability. Or one could choose to go with lower RDS(on) module like 8 milliohm TNPC, which would have lower conduction losses but same total losses as 11 milliohm and can benefit from lower junction temperatures to offset aging. Similarly, we have also simulated a 50 kilowatt dual active bridge topology using our 4 milliohm half bridge module for primary and 3 milliohm half bridge module for secondary. The simulation conditions are shown in the table on the left, where the output voltage of 800 volt DC and switching frequency of 100 kHz were used. Heatsink was the same temperature as before. The power loss data is also shown in the table here. The key thing to note is that the total losses were around 570 watt with the power stage efficiency of 98.96%. Within the 570 watt, 80% of the losses were switching losses. Hence, it's imperative that designers pay attention to technologies that can offer lowest switching losses possible for EV charger applications. Since onsemi's M3S also offers low COSS, low resonant inductor can be used for better system cost. Of course, in the simulation, we used a single stage concept for DAB, which is simple in implementation and can get you a reasonable efficiency in power stage. However, a dual stage approach is doable as well. A series parallel approach can offer a wider voltage and efficiency plateau but complex to implement. It could yield similar or better efficiency but additional cost in the form of relays switching from parallel to series connection depending on the vehicle battery voltage. When we think about megawatt charging system, traditional CCS or NACS may not work as this can only offer charging power up to 400 kilowatts. As we now move more towards megawatt charging for heavy duty vehicles, the same charging standards may not apply. So let's look at a little bit of math here. Based on Tesla Semi's efficiency metric of 0.5 mile per kilowatt hour for heavy duty vehicles to achieve 250 mile range, the battery capacity would have to be nearly 500 kilowatt hour. When a vehicle has such a large battery capacity and to reach 80% state of charge in under 30 minutes, this would require quite a bit of power. So for a similar 500 kilowatt hour battery, a charging power of roughly 1.2 megawatt would be required. In terms of design, megawatt charging systems can be powered up to 16 megawatt with a single point of connection to the grid. And each of these MCS can have multiple multiports that can power up these heavy duty vehicles, which are considered loads. However, these multiports also offer a multitude of functionality. These power conversion systems interface with not only loads but also assets such as energy storage and photovoltaics. So the table on the right bottom should give you a clear idea in terms of what each of these different loads and assets do in an MCS. One key thing I would like to highlight here is the requirement of high voltage devices such as silicon carbide 2 kV MOSFET, which will act as a key switch element that will be used in both front-end systems and also in DC-DC systems. This is still an area that is very much in emergence today. In addition to having a comprehensive silicon carbide portfolio, what sets onsemi apart from other silicon carbide suppliers is our vertical integration capability. onsemi has the silicon carbide substrates in-house at our Hudson, New Hampshire. We are capable of both 6-inch and 8-inch substrates from this facility. Wafering is done in Rasnau, Czechia. Silicon carbide epi is done in 2 locations today, Rasnau and Bucheon, South Korea. Our front end is also located in the same Bucheon facility in South Korea. Currently, we are high volume manufacturing in 6-inch substrates and we plan to move to 8-inch in the near future. Our entire backend, both discrete and power modules, are in-house as well. We have several backend locations in China, Malaysia, Vietnam and Philippines. Very few silicon carbide suppliers can boast end-to-end capabilities or decades of industry know-how or leveraging customer relationships in silicon MOSFETs and IGBT technologies. System power is increasing for the electric vehicle chargers as the vehicle battery cost and capacities are increasing and the requirement for lower charging times. In addition, there is also increase in efficiency standards as well. More than 98% system efficiency is becoming standard. For higher levels of deployment, cost-focused developments are also increasing with more competition. Finally, there are multiple use cases such as bidirectional vehicle to grid and vehicle to home, and attachment of energy storage and photovoltaic integration is also becoming standard. Newer approaches at the architectural level such as centralized front ends but then have distributed DC-DC stages at the charge dispensers is also becoming common. At onsemi, we have developed a 25 kilowatt reference design, which is a bidirectional three-phase solution using exclusively onsemi components. Secondly, we have developed new Gen 3 MOSFET based eval boards for half bridge, full bridge, and multi-level TNPC topologies. For more information, please refer to the QR codes shared on the slide. These modules can deliver from 50 to 75 kilowatt system power, enabling current generation EVC power blocks. Lastly, allow me to highlight onsemi's Elite Power Simulator and self-service Plex model generator, allowing customers time to market and maximum flexibility in determining right solutions for their applications. All the silicon carbide and FS7 IGBT products can be found in this simulation tool. With that,